Today we are going to see the delta function potential for bound state and scattering state for delta function well. In this lecture, we are going to see only for the bound state. In the next class, we will see for the scattering state. Before going to see the delta function potential well, we will see the basic property of a delta function. Delta x by definition is equal to infinite plus infinite for x is equal to 0. When x equal to 0, this will be infinite. And for non-zero value, if x is not equal to 0, then it will be 0 with the condition that the integral over minus infinite to plus infinite delta x dx is equal to 1. That is, this is the delta function. If you take this area under this curve, it must be 1. So this height tends to infinite and width tends to close to 0. So if you take the product height and width, you will get 1. uh, Let us consider the potential of the form V of x is equal to minus alpha delta x. Then and the Schrodinger equation for delta function well is minus h cross squared over 2m t2 psi over tx2 minus alpha delta x psi. Here I have replaced V by minus alpha delta x, which is equal to E psi. The above equation yields both found state and scattering state. When E is less than 0, that is E is negative, then it is found state. When E is positive, that is greater than 0, then it is scattering state. So, as I said in this class, we are going to concentrate only on found state. Let us take the Schrodinger equation for square well potential, that is, delta function potential, which is equal to minus h squared, h cross squared over 2m t2 psi over tx2 minus alpha delta x psi, which is equal to E psi. Now here the interesting thing is delta x will be 0 when x is greater than 0, as well as when x is less than 0. So in both cases it will be 0 other than x equal to 0. So this get cancelled. This will be 0. So you will get the delta 2 psi over delta x2 is equal to, I have brought this to the right hand side, which is equal to minus 2m over h cross squared. Already there is E and psi, E psi is there. Now I have shown some parameter inside the rectangular red color box, that is which is equal to 2m over h cross squared E psi. I have included negative sign also here. So this I am calling as k squared. Sorry, this is k squared. The terms inside the red color box is k squared. Then if, k is equal to square root of minus 2me over h cross, because if you take square root of h cross squared, you will get h cross. Here I brought negative sign inside the square root because here in the case of bound state, energy is negative. So this negative and this negative will become positive. So square root is a real number. Uh, then I can write this equation T2 psi over Tx2 is equal to k square. So what is the general solution? General solution must be in the form of ignore this normalization constant, where it is equal to plus or minus x kx e power. So if you differentiate this twice, you will get k into k square e power plus or minus x, which is nothing but your wave function. So k squared psi. So this general solution will be e power plus or minus kx. So with normalization constant, psi of x is equal to a e power minus kx plus p e power plus kx. If x is greater than 0, that is the case. Remember that I like to explain this point. Except this point, let us say this is minus epsilon, which is very close to 0. This side is plus epsilon, which is also close to 0. I have taken a delta function, which is rectangular in shape. It need not be rectangular. I have taken for simplicity is rectangular. The height is close to infinite and width is close to 0. Now we will see about the wave function. As I said, uh, in the case of positive x direction, this is psi of x is equal to a e power minus kx plus p e power kx. Since it's a positive, when x is infinite, then this will go to infinite. It's not a square integrable. So wave function must be finite. If you put x here in the second term, this will be infinite. So naturally, the p must be equal to 0. Here p must be equal to 0. So naturally, you will have only one solution in the right hand side. That is a e power minus kx if x is greater than 0. So that's what I have written. Ignore the origin. Then this wave function will be is an exponential one. So, similarly, what will happen in the negative x direction? In the negative x direction, the wave function will be c e power minus kx plus t e power kx. So, here also, if we apply the same rule, when x is infinite, minus infinite, then this will flow up. Because minus of minus infinite become plus infinite, the first term will become infinite. So in this case, C must be equal to 0. Only this term exists. That is psi of x is equal to t e power kx if x is less than 0. So this side, this will be exponential plus exponential. Sorry, 1 minute. This is equal to, I'll draw to this scale. This is plus exponential. You can see this is a e power plus x, a e power minus x. Uh, why here you have t? When x is equal to 0, this sign, in order to have a continuity, psi of x is here at 0, psi of 0 must be equal for both sides. So if you put x equal to 0, here also x is equal to 0, psi of x at 0 on both sides must be equal. That is a e power I minus kx, which is equal to t e power plus kx. When x is equal to 0, a is equal to t. So a and t are the same. I have taken both sides a e power kx, here a e power minus kx. So as a is equal to t. In the just now we have seen the solution for the case of x is greater than 0 or less than 0. That is, x is not equal to 0. That is in this range where x is equal to x is greater than 0. Here x is less than 0. X is, sorry, x is less than 0. So now we are going to find the solution at x is equal to 0. As I said, this is minus epsilon, which is close to 0, up of course in the negative x direction, and this is plus epsilon, which is also close to 0 in the positive x direction. We know that we have seen that Schrodinger equation for delta function potential is minus h cross squared over 2m T2 over T2 psi over Tx2 minus alpha delta x psi, which is equal to E psi. Previous case, that is when x is greater than, when x is not equal to 0, we have taken this as 0. Now we are going to take when x is equal to 0 or close to 0. Remember that there is a discontinuity at x is equal to 0. At x is equal to 0, this slope, that is a derivative, is not zero, it's infinite. That is one of the property of wave function is the wave function and its derivative must be continuous at the boundary. So here there is a discontinuity. Then how to solve it? Because here t psi over tx is infinite. So we can solve it by taking integral of this one. Because you know the from the delta function property, if you integrate this between the limit minus epsilon to plus epsilon, you will get 1. So you integrate this. So minus h cross squared over 2m is a constant taking out, and integrating between minus infinite to plus infinite, sorry, minus epsilon to plus epsilon t2 psi over tx to tx, and minus a second term alpha is a constant I am taking out, integrating over minus epsilon to plus epsilon delta x psi tx, and left hand side I am taking the integral, e is a constant I am taking out, and I am integrating between the limit minus epsilon to plus epsilon. Now we will solve one by one term. First, you take the right hand side because it's easier to solve. E is a constant I have taken out. The wave function psi of x, here if you apply the limit lower limit also close to 0, upper limit also 0. For practical purpose, you can take as 0. Then wave function will be 0. This term will be 0 because between the limit 0 to 0. So I can take right hand side as 0. Now I will get these first two terms, that is h cross squared over 2, first two term I will get. Now you multiply this by minus 2m over h cross squared. So the first term you will get 1 here. Here you are multiplying by 2m over h cross squared. So there is a minus 2m over h cross squared. So this will become plus 2m alpha over h cross squared, because already there is alpha, and as usual this integral. So now you bring this second part to the right hand side. Right hand side already 0, so this will become minus. Then you integrate between, when limit tends to 0, the upper limit is, if you integrate the second order derivative, you will get naturally the first order derivative. Of course, you have to apply the limit. So upper limit is epsilon and lower limit is minus epsilon. Of course, both is close to 0. Then you come to left hand side. You brought this term to the left hand side, which is equal to 2m alpha over h cross squared, and this integral limit epsilon tends to 0. This delta function, delta x psi of x, of course psi is a function of x, tx. So this integral exists only when x is equal to 0. Under all other conditions, it will be 0. So for non-zero value, it is 0. For 0, it is 1. So naturally, psi is a function of x. So if you integrate this between the limit 0, you will get psi of 0. Uh, so this will become the left hand side, sorry, right hand side will become minus 2m alpha over h cross squared psi of 0. So now we will solve this further. So we got this expression. Now we know the wave function at positive x direction we have seen, which is equal to a e power minus kx if x is greater than 0, and if it is equal to a e power plus kx if x is less than 0. This is positive x direction, this is negative x direction. If you differentiate this, then you will get uh, minus k a e power minus kx. Similarly, in this case, it is plus k a e power kx. Now you subtract this dy by dx at positive epsilon, that is this one minus this one. Remember that minus ka e power kx. This is minus ka e power minus kx, and this is minus 2m alpha over h cross square. This one into psi 0. Psi 0 is a power. This 0 point is boundary point, that is between positive axis and the negative axis. So the wave function will be e power plus or minus kx. Here you can see e power kx. I will use the different color. So this e power ikx, when x tends to 0, e power 0 is 1. Same is the case with this exponential. So this is equal to 1. Similarly, this is exactly at midpoint, that is x equal to 0. This also will become 0. So now you have minus ka, which is equal to minus 2 ka. And this the right hand side you will get minus 2m alpha over h cross squared a. Now you can cancel out this a and a will get cancelled, and this minus 2 and minus 2 will get cancelled. So you will get right hand side k and left hand side m alpha over h cross square. This is normalization constant. Uh, so this normalization constant is equal to k equal to m alpha over h cross square. So we have seen that k is equal to m alpha over h cross square, which implies E is equal to minus h cross squared k squared over 2m. So you take minus h cross squared over 2m outside, then k squared is equal to m alpha over h cross square. See here h cross squared, square of square. So one h cross squared cancel with this one h cross square. So ultimately you will get h cross squared in the denominator. Similarly, in the numerator you have m squared alpha squared. Here m squared will get cancelled with this m. You will get simply m in the numerator. Of course, you have alpha squared. So if you simplify this energy is equal to minus m alpha squared over 2h cross squared. Remember that unlike harmonic oscillator or infinite square well potential, there is no n. There is only one state in the case of uh, delta function potential, only one state. There is no n. So m alpha squared minus m alpha squared over 2h cross square. That is a very important point. Irrespective of strength of the delta function potential, alpha may be any value, but you have only one state. You will get this E is equal to minus m alpha square over 2h cross square. Now, next task is you find the normalization constant. For normalization constant, minus infinite to plus infinite, size modulus psi squared Tx is equal to you know that this wave function is a into e power the wave function, you know, a into e power minus kx in the positive x direction. In this direction we have. So then if you square it, you will get e power minus 2kx. This 2 comes because we are changing the limit minus infinite to plus infinite by 0 to infinite. Now if you integrate this exponential term, uh, you will get 2a squared. This 2 comes, as I said, because of change in integral limit. 2 modulus a squared. If you integrate this exponential term, you will get e power minus 2kx divided by minus 2k within the limit 0 to infinite, which must be equal to 1. If we apply the upper limit, e power minus infinite is 0, and if we apply the lower limit, e power 0 is 1, so minus 1 you will get. Already there is minus 2k in the denominator. So this will become 2a squared minus 1 divided by minus 2k. Here, this minus minus will get cancelled. This minus and this minus will get cancelled. So you will get similarly this 2 and 2 will get cancelled. So you will get a squared over k. A squared modulus a squared over k is equal to 1. Then naturally a is equal to square root of k. So where square root of k is, you take this square root of m alpha over h cross. So as I said, the energy level is one. You have only one energy state, that is E is equal to minus m alpha square over 2h cross, and the wave function is normalization constant, that is square root of k into e power minus kx. Here we are taking m alpha over h cross, this k x, we are taking modulus x because we are taking both right hand side and left hand side as a common wave function. So if you take right hand side and left hand side, this will be modulus x. So even if it is negative x, you will get positive x only. So when at point 0, that is x is equal to 0, e power 0 is 1. So this maximum peak you will get at square root of k, and this is your wave function, square root of k into e power minus kx, where square root of k is normalization constant. In the next class, we will see about the scattering state. Thank you very much for watching my video and supporting me continuously. Thank you very much.